Welcome everyone to this last talk of the 8th edition of the Legacy of Socrates. With me is Jay Bazuzi. And little introduction, if you don't know Jay, personally is one of the figures that inspire me, along with Llewellyn Falco and Arlo because the three of them, they are digging into topics that are quite unique and very concrete, such as provable refactorings, the risk assessment in the commit notation, stuff like that. I attended to a workshop that Jay and Llewellyn were doing on refactoring gnarly legacy code with others as an ensemble remote programming. It was quite a fun experience. And I was like, yeah, come on, there is no way you can refactor this code without test, except that sometimes you have to because you need to refactor the code before you can add the test. And what do you do to reduce the risk? And I learned a ton of things. So I'm really glad that we're tackling this topic now. I don't think we ever really mentioned how to refactor existing code when you don't have tests. And Jay is going to show you that right now.
Hi, my name is Jay Bazuzi, and I'm a programmer and technical coach. I love working with legacy code and feel really at home here at Legacy of Socrates. I'm talking today about how we use safe refactoring to untangle gnarly code without tests. I'm supposed to tell you that I'm employed by Salesforce, but don't represent them in this presentation. It's just me talking. On the left is a QR code back to the slide deck. This isn't your last chance to get the slides, but if you want to take a pic now, go for it. In the middle is my Twitter handle. I would love to talk with you about refactoring, legacy code, testability, and so on. On the right is what looks to me to be a maple tree that grew out of a dead madrona tree. This past summer, I discovered a love of hiking, and that's where these pictures come from. The pictures in this slide deck don't mean anything about the message of the presentation. I just like them. I put them on my rambling slides to give you something nice while you listen to me. The talk right before mine was Claire Sudbury talking about let's stop making each other feel stupid. Her talk is more important than mine. For a long time as a programmer, I largely missed the fact that software is written by people for the benefit of people. How we treat each other as we work together, how we write the code that we'll live in the future, how users experience the software we create, and how it changes the world. All of these are about people. Making software well is an act of empathy as much as it's an act of engineering. I think this applies very much to the testing and refactoring topic I'm talking about today, but it also applies to everything else we do. Let's care for the people. Have you ever been trapped in this loop? We have gnarly legacy code that we want to clean up, but we can't clean it up safely without tests. And we can't write good tests without refactoring the gnarly code. But we can't. Oh. This picture shows a boardwalk through some wetlands. I didn't feel trapped when I was there, but it does look like we're between things. Not meant to be a metaphor for the slide, but there it is. There are lots of good reasons we might want to refactor gnarly legacy code safely without tests. We might want to make the code more readable. It's hard to do much in code we can't read and understand. We might want to reduce duplication. We all dislike redundancy in our code, and cleaning it up first just makes everything else easier. We might want to improve modularity, so teams can work separately without stepping on each other's toes. In a large project, we might do this first, so each team can take responsibility for cleaning up their own code, closing the incentive loop for that code. We might want to add extensibility to make it easy to plug in our next feature. And we might want to make the code more testable, and then add good tests. Any of these problems might be the one you want to address first, before you have tests. There are ways to address any of these design problems with safe refactoring without tests, but today we're going to focus on testability. The idea is that once you get testability, you can add tests and create a safety net, breaking the vicious cycle mentioned on the previous slide. If you're interested in the other topics, let's talk about making a presentation for that another time. Here in this contrived example, we have a function that takes a big class that is hard to create in the calling test. Before we can talk about how to refactor safely without tests, we need to know what we're going to refactor. So let's refactor to make this function easier to test. To test the function as is, we would have to work really hard to pass in so many arguments that are hard to supply but not important for this test case. There are irrelevant but required objects, nulls for objects that don't matter in this case, and a bunch of uninteresting booleans for good measure. Not only does this make the test more difficult to write, it's also hard to read, and the test can now fail due to unrelated defects that only affect the setup code. We're going to apply what Llewellyn-Falco calls the peel strategy, extracting most of the body of the function, leaving just the first line behind. Give this new function the same name as the original. It has the same responsibilities, it just takes different parameters. So it's an overload with the same name. This new function is much easier to test because we only have to pass in foo. We sometimes talk about the dependency inversion principle as part of solid, but this is something different. This is dependency elimination, or at least reduction. This picture was on a hike where I learned that huckleberries like to grow in stumps. I had never seen them in the wild before, and after this, I saw them everywhere I looked. Something similar happens when I learn code smells and refactoring opportunities. Once I learn to see them, I can't not see them. Again, this wasn't supposed to be a metaphor, but when I put it that way, it sounds fitting. I've shown a refactoring that improves testability, but I promised safety. I promised that you can do this refactoring without a safety net of tests in place. How can we do that? In some languages, we can use automated refactorings that compile the program and use a semantic understanding of the code to execute the refactoring correctly. If you have reliable automated refactorings available to you in your language, you should definitely lean on them. These refactorings are so desirable to me that when I choose a language for a project, I will look first for a language that has reliable refactoring tools available. For example, I'd rather not use Node.js because JavaScript is so hard to refactor safely. To the authors of refactoring tools, I wish I could ask you to write refactorings that either work correctly or reject my refactoring request. I don't need automated refactorings as a productivity tool. I need them for, no matter how bad the code is, please do the right thing. Maybe if I could wave a magic wand over my IDE, I would make a safe mode. When not in safe mode, all of the productivity tools are available. But in safe mode, only reliable code transformations are available, and I could use this when untangling legacy code. Let's take a look at an example with C# in Visual Studio. As we do this, remember, we're not looking much for good design, but for safety and testability. This long function takes a bunch of parameters, and 4 of them are only used in this one spot. I don't know much about the rest of this function. We haven't tried to read it yet, and we're not here to improve readability. Let's peel to simplify the function's API to make testing easier. We'll select the rest of the long method. Ooh, I've zoomed out, and there's still more code to select. Finally, I have zoomed out enough to select the whole function. There's an important point here. This function is hard to understand because it's so long. If I wanted to use regular code editing to make this code more testable, I would probably make a mistake somewhere. It's too complicated for my small brain. We're not here to fix long functions, though. Maybe next time we come across this, we'll deal with that problem. Maybe at that time, we'll be glad for the test we're getting ready to write. Visual Studio has an excellent extract method for C# that is very reliable, very safe. Visual Studio understands the incoming and outgoing data, how to handle early returns, breaks, and continue, etc. I had the privilege of working with the team that developed the C# refactorings in Visual Studio, and they were very deliberate about making them work correctly, so I trust them. Here we have completed the extraction. You can see that the old function is just a simple call to the new function with slightly simpler parameters. I will commit each change to source code by itself, to source control by itself, with a description saying that it's a refactoring. The R prefix indicates a safe refactoring, and the T prefix means it's a test-only change, which is also safe. Test changes can't change production code. Both can be merged to main and shipped to production at any time. This is a great benefit of safety. The prefixes come from Arlo's commit notation, which deserves its own talk on another day. This is a picture of a frog. Or maybe it's a toad. I have no idea how to tell them apart. It's great when we have powerful, trustworthy refactoring tools like those available for C#, Java, Kotlin, and so on. But what about a language where the refactoring tools are inadequate? There do exist refactoring tools for C++, but in my experience, I can't count on them to get all the details right. And since we're working without tests, we need more safety than that. This recipe gives step-by-step instructions for extracting a function in C++, relying on the compiler to verify correctness at key points. I'll show you how it works, but if you need to do this for real, follow the linked recipe. This hike was on a hot day, and we ran out of water and got delayed waiting for one of my kids. I brought my water filter with me, but wasn't sure if a filter handles whatever an insect like this might mean for the water. I looked it up, and I think it's a caddisfly. They attach things to their bodies, like these little pebbles. They are sensitive to pollution, so their presence indicates clean water. I bet you could make a coding metaphor about that if you wanted. Back to the code. I'm using simpler code this time to make it easier to follow. In this code, the first couple lines are in the way of testing. We want to extract the remainder into a new function. First, we surround that chunk of code with this line noise. This creates a lambda and immediately calls it. And we'll compile to verify correctness. Then we assign the lambda to a variable. Compile again. Now we remove the ampersand to block capturing. The ability to specify capture rules for lambdas is an unusual language feature that fits right in with the philosophy of C++, but I haven't seen it in other languages. This creates a compile error, which will guide our next steps. We can compile just this one file, which is way faster than building everything. Take a look at the compile errors. Each error about a variable indicates data that flows in, through, or out of this block of code, which we need to accommodate. We can get the program compiling again by capturing each of these variables explicitly. Again, it makes sense to me that you can do this in C++, but it would be strange for most other languages. Then we convert the captures to parameters. Mark each as auto to keep things green. To make the types explicit, copy from the variable declarations to replace the uses of auto. Add the return type. See the recipe for more details about where that comes from. And then we extract the lambda out of the current function and give it a new name and its own standalone function. It's been extracted and it's easier to test. One thing to note about this recipe is that it was a series of small transforms that each preserved the behavior, a series of tiny refactorings. We could have committed each one separately. That can be useful when the code is especially gnarly, so you can checkpoint your progress and make it obvious to a future reader that you followed the recipe. You can also deploy each checkpoint to production separately if that's useful in your context. I like deploying safe refactorings to production because when I next ship a real change, if it breaks something, I don't have to roll back as far to get things working again, and there's less churn to diagnose. That was a lot of work. Why do all that just for safety? Why not just edit code? We developers edit code all the time. We try to be careful, but sometimes we break things. Then we fix the bugs and move on. Why doesn't the same approach apply to refactoring? Why jump through so many hoops? If I make a mistake while writing a feature, everyone will be disappointed, but no one will say, we should stop writing features. Maybe we should be more careful. Maybe we should test more, but we'll keep writing features. If I make a mistake while refactoring, the business will see a downside with no upside. It's hard for non-programmers to see the value of refactoring, but it's easy for them to see the cost of defects. So they'll be inclined to say, we should stop refactoring. This is really dangerous for the long-term health of the business. If we refactor less, the code will get worse faster, and all the design problems we described above will grow faster. Velocity will slow and defect injection rate will increase, leading to worse quality, which is what we were trying to avoid by limiting refactoring. This is terrible for the business, and it's up to us to make sure it doesn't happen. In this picture, we see fresh beaver activity. The chips on the ground were bright, so this must have been very recent. I think it's so cool that I live near beavers. Just a few blocks away from my home, a beaver was relocated because it was trying to reorganize the waterways in our local park, and it would be difficult to use the trails if the beaver flooded them. I guess that's kind of like the business telling us not to refactor. Really, this wasn't meant to be a metaphor, it just turned out that way. Anyway, please refactor responsibly. All right, let's talk about another testability problem. In the first examples, the code was laid out in a way that made it easy to extract a function and leave the coupling behind. But suppose your code has a nasty, difficult to test interaction right in the middle. We can't just extract a function like we did before. In this case, we're retrieving volatile data right in the middle of the function, so we can't reorder to move the coupling to the top and apply peel like we did last time. We need a different approach, which Llewellyn Falco calls slice. First, we'll extract an immediately invoked function expression. You may recognize this pattern from the C++ extract function recipe before. You can extract an IFI in most modern languages, and it's often straightforward to do it safely by hand, even if you lack refactoring tools. In this hypothetical language, we add some parens and stuff. If it compiles, it's legit. Then we extract a variable. Again, in many languages, this is safe enough to do by hand, as long as it compiles. Notice that we haven't changed the order of execution of anything. Now we can reorder the statements to pull the lambda up to the top. Even though the statements are laid out differently, still, the order of execution is the same. This is often safe to do by hand in most languages. Now we can extract function, similar to the peel example that we did before. Here is the result. As you can see, the testability blocker is resolved. Is this a good design? Maybe. There was some coupling before, which we have severed, but it's not clear whether we have severed in the right place or in the right way. At this point, I like to ask whether we're missing an interface, especially if we have two or more such lambda parameters. There's a good chance they go together on a missing object. These are important design concerns, but I'm going to set them aside for now while we focus on testability. As Arlo says, the goal today is better, fast, not good. If you want more about making this coupling point better, let's make another talk for a future event. This lake was growing honest-to-goodness lily pads. I think they grow in every summer and die back every winter. That's kind of neat. You might be wondering about what we have left untested in this example. Should we test get volatile data? Should we test this glue function that is only 2 lines long? And how should we test them? I like to frame that question as, what are the things we might get wrong? What bug might we introduce which we hope a test will catch? We need to know what the hazard is that we're trying to remediate. For get volatile data, let's imagine that it calls to some external service that we don't control. Maybe it asks for the weather so I can decide what to pack for my next hike. That is pretty volatile data. There are two kinds of mistakes I might make in that function that I would want tests for. I might misunderstand the contract with the service and call it incorrectly, or interpret its results incorrectly. My code is doing what I intended, but my intention is wrong. You might be used to testing with mocks, but a mock in this situation would not be helpful. The mock would encode my same misunderstanding that I'm trying to test for. My test would pass, but my system would still be broken. The risk here is about integration defects. So the only valid way to test is with a real integration test. It can be a focused integration test that only tests this interaction with this service, but it can't be a unit test. I'll back it up by pinning this code with a VCR test. A VCR test makes a recording of requests and responses, so you can repeat a test in isolation. It's not a substitute for focused integration testing, but it's a good way to tell you when you've changed something and need to rerun your focused integration tests. The other possibility is that I might correctly understand the contract with the service, but implement it incorrectly. I might make a coding error. This is a local problem, not an integration problem. If this can happen, I need to refactor to separate the hazardous containing local code from the difficult to test integration code using the same techniques we've been discussing here. This picture on the left might help. There's a large application containing your business logic. There's an external dependency in the bottom right. Your app defines a port, and an adapter sits between the port and the real external dependency. Your focused integration tests go through the port to test the adapter with the real dependency. The VCR system records the requests and responses and plays them back at unit test time. About the picture. Sometimes on the trail, I can only see what's right behind and ahead of me. Everything else is forest. At this point, the forest is open and I could see across to the other side. That totally sounds like a metaphor, but for what? For the original f, which was a very short glue function, my answer to whether to test it is, it depends. As written, it's very simple and would be difficult to get wrong, so you might decide it doesn't need tests. If the return type of get volatile data is a dumb struct, and you're in a compiled language like Java or TypeScript, or are using Python with MyPy, maybe all the tests you need to be confident that things are wired up correctly is running the compiler. If it feels like it needs more tests, this suggests that it's not just glue code and contains business logic. Refactor to separate the business logic from the glue in the same ways we've been talking about. This picture was the first time I noticed ferns growing out of the side of trees, even really high up. I thought ferns only grew on the ground. Let's step back and see what we've covered today. We've talked about ways to peel and slice difficult to test functions to make them more testable. We've done it in a way that doesn't rely on tests for the safety we need. We've done it both with and without great refactoring tools. There are other reasons code might be difficult to test. Arlo's article linked here is a good catalog of those cases, with some ideas about how to approach them. Once the code is more testable, we can more easily build out a safety net of tests and use that to combine both test-protected manual edits and automated refactorings. The first link is recordings of Llewellyn and me refactoring gnarly legacy code using a combination of manual and automated transformations and Arlo's commit notation, if you want to see what that looks like. You may know the classic song New York, New York, which begins, "Start spreading the news," and ends, "If I can make it there, I'll make it anywhere." Today's techniques are about the most difficult cases, the gnarliest code, the longest functions, with lots of unknown callers, and a lot of business value riding on the current functionality, including functionality I'm not aware of. This is when I need tools that don't depend on me being smart enough to reason about the code correctly. If you're in an easy case, you may decide not to bother with all this rigmarole. But remember that refactoring is held to a higher standard. Don't make the mistake of giving the business a reason to discourage refactoring. In this picture, the water level of this pond is higher than the ground next to it, about waist height. That was cool. Maybe your brains are full like this pond. I couldn't end this talk without mentioning some of the other great work that others have done in this space. Obviously, Michael Feather's book, Working Effectively with Legacy Code, is the premier book on the topic, and you should definitely take it in. We've had a lot of new insights in the decade and a half since it was published, which all owe gratitude to Michael. I've already mentioned Arlo Belshi. Deep Roots is his company, which specializes in whole company transformations around legacy code. And of course, all the great presentations at Legacy of Socrates, now in its 8th iteration. Wow. And that's the end of my presentation. Any questions?
Thank you very much. I love how concrete that was, and you also referred to links to other topics that people can really dig into. The comment notation, for instance, we do have a question for this. I'm gonna read that now. Okay, so that's actually the first question. When did you pick up Arlo's commit notation, and do you recommend it to every developer?
All right. So I've been doing something like Arlo's commit notation for 15 years or so, but it continues to evolve. And one of the things I've noticed is there's a lot to it. So now that I'm well accustomed to it, I really like using it. But to get started, what I would recommend is first just getting in the habit of breaking up your changes, looking for incremental steps to commit by themselves. They don't have to be disciplined in the way that we've been talking about here. You don't have to identify which are refactorings. Just learning to call out the steps, that takes some effort to learn. And then once you've learned that, identify just refactoring commits and tag them. So Arlo has a notation with R. That's a perfectly good notation. I would say spend some time getting used to calling out refactorings. One benefit for me is that when I'm looking over my changes so far, they're easier to understand. And then when I send out a code review, the code review is easier for the next person, or pull request, or whatever your context is. If you've ever been in a situation where you send out a review request and it takes a full day before you get a response, I want my responses quicker. I want to get my work done. And I figured out that if I can break up my changes, use a lot of disciplined refactoring, and call out the refactorings with these kinds of tags, I can get my reviews back faster. So it's both a way of helping my reviewer and a selfish thing to help me get my work done. And just that set of changes to my workflow results in a huge benefit. After your team has gotten used to that, that's when I would go back and look at Arlo's commit notation and think about what are the other parts of that system that we're ready to pull in.
That's awesome. Thank you very much. The next question is, do you have a worked example for a VCR test and or focused integration test?
Yeah, that's a good question too. So for VCR testing, there are VCR libraries. I've seen them for C Sharp, Python, Ruby. I'm assuming they exist for other languages. If you just search for that, they'll come with some examples of how to do it. But I do think we need more examples for that. And then as far as focused integration, I don't have good examples for that. And it's kind of a tough one. To give good examples, we need a program that is big enough that you really need the extra structure that comes with carving out adapters and identifying ports and having different kinds of tests. So for a trivial program, the example would feel too heavy. But as soon as we make the program big enough that that becomes interesting, then the example gets hard to read. And for examples, like look at the code I showed today, I said 3 lines. That's probably plenty for a slide. So it's really hard to find good examples. But I would like to. Maybe what we can do is find some code that is complicated enough and work through a refactoring, maybe a Twitch stream that we'll record, and maybe that will be useful to people.
Yeah, I think the format of a talk like this with the presentation, you have slides, you need to show that. You cannot have such a work example. But yes, an actual small and little application, but complex enough, could be a good example to test. And for VCR, yeah, if you look for VCR, you will find it for different languages. For JavaScript, I know one at least. I will share that in the chat. The next question is, who guarantees the adapter validity? So it's related, like, how do you verify the adapter works well?
Yeah, so there's a few different parts to that puzzle. The first is I'm going to use real integration testing for my adapter against the real service. And as I was saying, that's the only valid way to test an adapter, is to test it against the real thing. And then I'm going to run those integration tests as often as feels comfortable. So if you think about querying the weather, if I ran that with every edit build test cycle, that would be too noisy with the weather changing. Couldn't run the test that often, but I might run it on a daily basis. Maybe it requires a little manual inspection to verify that it's correct. So for each dependency in my system, I'm going to look at what makes this dependency difficult to test and how often can I run that test. And maybe it's on every CI, maybe it's nightly, maybe it's weekly, maybe if you don't ship that often, it's quarterly. But I'm going to have a comprehensive set of automated tests for that adapter. They're just not unit tests. And then I'm going to back that up with the VCR like we talked about.
Oh, sorry, yeah, I was answering in the chat too. But yes, exactly. I think G.B. Rainsberger had some talk, not concrete example, but some talk, and maybe a concrete example on contract testing as a way to, do an integrated test of all of these implementations of all of the different adapters. So it uses that to show that you can replace um, the actual adapters that is doing the call to the third-party service with an in-memory one that you have implemented that you can use to test the rest of the application in isolation. And it uses the same test suite on both implementations to verify that the behavior is the same.
Yeah.
Maybe something to dig into.
Yeah, I like that strategy a lot. Once I have the set of tests in place for my adapter, I can run those same tests against that in-memory system as I develop it and make that available for testing my application without the real adapter. I've seen that called simulators. Sometimes all these names go together as ports and adapters and simulators. Although I don't usually call it that because that makes it sound like it's a testing strategy using simulators. And it's a design strategy first to separate concerns that are my application from concerns that are integration. And that's what matters to me most. So I don't usually call it that.
Yeah, I understand. But as Barry showed earlier, often good code, like easy to test code, easy to use code is also easy to test code. There is a link between testing and software architecture for sure.
Yeah.
All right, fine. We have one question left, which is, would you keep very granular refactoring commits with annotations in the repository, or do something like merge them from a branch and squash everything with a summary message rather than all of these little commits at the end?
Yeah. And part of that question is how noisy will I let my commit history be? I refactor really quickly in tiny steps. And if all you can see is just tiny change and a long stream of them, it can be difficult to follow the history. So one thing I like to do, if I can, is find some way to clump them together. So most people today work in Git. So we'll talk about it as a Git example. If I start my effort with the very latest from main, I make a branch, and then in my branch, I go commit really quickly in tiny steps, and then I merge back to main. If you look at the shape of that Git history, it shows up as a clump. You can make the merge at the end, name the clump, the overall arc of the changes. I have some examples, but I didn't prepare any to show off today. Part of what makes that work well is the assumption that nobody else has touched main in the meantime, and I haven't merged anything new from main into my branch. So it gives a clean history with only a single merge commit. To do that requires a little bit more Git knowledge. Um, Anybody can learn it, but you might not already be showing up with it. And so it's going to depend on my team and the tools that are available and the kinds of changes we're making. But I do really like to find a way in my source control to say, here's a dozen tiny commits that all roll up together to this one larger effort. One thing that makes this a little easier is if I'm working in a safe way, I can merge back to main sooner than if I'm just continuing on my overall path until I finally get to completion. So suppose you're somewhere where most people check in once a day, because that's how the builds and what tests are in your context. I might be able to merge into main once an hour. So I'll sync up, do a series of commits, merge back into main and take a break, and then come back, sync up to main, make a series of commits, merge back and take a break. And in that way, you see these clumps that show the different arcs of the change.
Yeah, thank you for all of these insights. There is no more question, but there is one comment from Emily that I need to share with you. Love your hat, Jay, and all of the beautiful photos in your presentation. Thank you. And yeah,
Great.
same. It was a really cool format. And I learned a few things about the forest and natures on that talk. Yes. All right. So I think that's it. Yeah, there is no more questions. So we're gonna wrap up. Thank you very much, Jay, for being here doing that. And I know you have more topics that you could also cover. But that's it for today. That's enough. That's already plenty of knowledge that people can share and adopt. Adi,